Good morning, everyone. I'm Xiao. I'm honored to be here presenting our work, eDoctor, automatically diagnosing abnormal battery drain issues on smartphones. And this is joint work with my colleagues Peng, Huang, Xinxin, Soyeon Park, Dongcai, Shen, Professor Yuanyuan, Zhou, Professor Saul, and Professor Geoffrey Voelker from UCSD, and Peng Wang from Peking University, China. So as a well-known fact, smartphone has taken over personal computing. So ever since from 2 years ago, the sales of smartphone global-wise, it's surpassed the sale of PC, and smartphone sales still going very, very fast. And in the meantime, there are various other studies shows smartphone become very pervasive. For example, the recent one saying 3 out of every 4 US adults now having a smartphone. So smartphone is really great. It changed our lives. But however, is everything with smartphone going equally well? The answer is no. So the Sprint CEO once said, the biggest impediment to mobile growth is you got the processors are getting a lot faster, screens are getting sharper, and they use more and more energy. However, the battery technology is not moving very fast. So how exactly slow is the battery technology moving? Let me show you some data. So this is some data from about the battery density. So basically, the battery capacity is determined by battery density because the battery volume on smartphone is very limited. And this data shows over 14 years, battery density only improved 2.3 times. So I say it again, it's 14 years, 2.3 times. So it's very slow. So although it's starting growing faster in the recent years, but it's still not good enough. And because of this, there are a lot of research and industry effort has been devoted to improving battery lives on smartphones and in general mobile devices. For example, wireless networking technology, more energy efficient displays. However, these efforts are all really great, but they focusing on improving battery life on their normal battery drain. So what do I mean by normal battery drain? So in normal scenarios, the battery may drain fast because the user actually running some tasks which are by nature energy consuming. For example, navigation or playing video games, or the user just use the smartphone for a very long time. However, is everything about battery drain a normal scenario? The answer is no again. Because we observed actually there are a lot of battery drain issues are caused by abnormal scenarios. And these battery drains are sudden and severe, and the cause of these battery drains are mysterious to users. For example, they may be caused by software defects, bad designs, misconfigurations, and sudden environmental condition changes. And more importantly, what we find is abnormal battery drain, short for ABD, actually dominates user complaints on battery life. We're not just saying this, we actually have data to back up. We randomly sampled more than 200 battery complaints from 3 major Android forums. And this figure shows the breakdown of their root causes. And interestingly, we find the normal usage complaint actually only account for 7.6%, which means more than 90% of the user reported battery drain issues are abnormal battery drain issues. And we have more details about the study in the paper, so I will not mention too much here. Let me give you a concrete example. What is abnormal battery drain? So this is the Facebook app. One of the updates has a wake lock bug, which will keep the phone awake even after the user uses the phone and even after the user closes the screen of the phone. And this bug will drain a fully charged battery as fast as 2.5 hours, as some user report. And the estimated number of users of this app at that time was 12 million. And we can safely assume a lot of users will be affected by this bug. And notice this is the official app from a big company, let alone some many other apps from small third-party developers. So, I mean, this is what users say when they say this is a big problem. And obviously, this type of battery drain issues make users frustrated. And it hurt user loyalty to the app and even the platform. And potentially, it also increased the cost of customer support. So by far, I hope I have motivated you. Abnormal battery drain is a big problem we need to solve. And here's the outline of the rest of my talk. So first, I will describe how the user will diagnose abnormal battery drain once it happens, and why it's very challenging for average user to diagnose abnormal battery drains. And followed by the design and the implementation of eDoctor, and followed by the user study, which we prove eDoctor actually works, and then I will conclude my talk. Okay, so we cannot completely eliminate abnormal battery drain. And in that sense, we need to help user to diagnose abnormal battery drain once it happens, and the user can prevent it from happening again. However, it's very, very challenging for average user to diagnose abnormal battery drain. Let me give you the example how the user would diagnose the Facebook app bug. So from the beginning, the user observes there's a battery drain on their phones. And then they need to use some high-level battery profiler. So this profiler called battery usage is a utility comes with all the Android devices. So they may find, okay, Facebook consumes most of the energy. And the next step, the user needs to ask herself, for example, do I use the Facebook app a lot or not? So if they use the Facebook app a lot, so Facebook app will always rank as the biggest energy consumer. So the user will get confused again. So if not, so the user may need to understand why exactly the current Facebook app consumes more energy. Then at this moment, they need a more powerful profiler tool to know what exactly happened. And there are several tools to do this, and they may find, okay, there is the Facebook app misuse a wake clock. And at this moment, the user also needs to remember she recently upgraded the Facebook app. Okay, now another question. Can we stop use the Facebook app? If we can stop, okay, we just delete the app, we don't use it anymore, then we don't have battery drain. However, this is not the often case. So usually people still want to use the Facebook app. So in that sense, one of the ways to solve this is we need to roll back to the previous non-buggy version of the Facebook app. However, it's not very easy. So the user needs to install another tool to pull up the old version of the app and install on the phone. And in the meantime, the user needs to have the access to the previous version, which is also not very easy. Or if the user cannot find the previous version, then the user needs to manually terminate the app every time they use the Facebook app, which is very tedious. As you can see, this diagnosis process requires the user to use 3 different tools, remember recent updates, understand how system works, how wake clock works, and have access to the old version, which is almost impossible for average user. And as we just mentioned, there are several existing tools which can help in certain extent, but they are not efficient for average user. For example, we have all different kinds of profilers, but they only provide limited information, and they cannot differentiate normal versus abnormal battery drains. And their information is hard to understand by average user. There are also some other tools which help users to configure their phones to be more energy conservative. However, they are not aimed to solve abnormal battery drain issues. So what's the ideal solution? So the ideal solution should be we have a black box. And once the user have a battery drain problem, and they tell the black box that we have a battery drain problem, and the black box will tell the user, okay, this is the reason, and this is how you need to fix it. So now I introduced eDoctor. We built this tool, so the eDoctor would it automatically diagnose abnormal battery drain issues and also help user, give user the suggestions how to fix it. So the eDoctor is based on 2 very important observations of how smartphones use energy. And the first observation is face behavior. So basically, the execution of a smartphone app can be divided into intervals. And each interval can be, and some intervals can be grouped into phases. These intervals does not have to be continuous. And in all the intervals in a certain phase, they share similar behavior. So in our context, which means they share similar resource usage behaviors. And the good thing about phase behavior is some apps, if the app has uncommon and energy-consuming phases, which make them a suspect of battery drain. So how to do the phase analysis, we explored 2 different strategies. The first strategy, we call it resource type vector. So basically, each execution interval is represented by a vector. And each element of the app vector indicates whether a certain resource is used in this given interval. And when we group vectors, when we group the intervals into phases, it's pretty straightforward. So each unique RTV will represent a unique phase. So this figure shows some data from a real user when they use the Facebook app. And we can see, so the lower part shows at certain intervals whether these 3 different resources that are used or not. And the upper part shows which phase each interval belongs to. As we can see, there are 4 different faces. However, in our experiments, we find RTV is not good enough because it misses some information. You can imagine 2 execution intervals. They may use the exact same type of resource. However, they may be very different in terms of the amount of resource they use. So based on this observation, we introduced another way to do phase analysis, which we call it resource usage vector, short for RUV. So similarly, each interval has 1 vector, and the element of the vector represents the amount of resource usage in that interval, not only whether the resource is used or not. And when we try to group intervals into phases, we use a k-mean algorithm to group the similar intervals into phases. And here again, we use the exact same data. We can see on the lower part, we don't use whether we use the resource. Instead, we use the amount of resource used in each interval. And from the upper part, you can see we find 5 different phases, and the phase switch actually more regular than the previous slides. So the second observation is we find most of the time abnormal battery drain happens after certain trigger events. So basically, the battery was normal before, and something happened, and the battery started draining very fast. And this trigger event is very important because if we find the trigger event, we know the solution. And the trigger event could be the user updated existing app, or the user installs a new app, or the user changes configurations, etc. So based on these 2 observations, we built eDoctor. So from a high level, eDoctor contains 4 different components. The first one is information collector, which runs as a service to collect all the information we need. And the second part called data analyzer, which periodically analyzes raw data and build a phase table for each app. And finally, we have, and the third part is diagnose engine, which is in charge of once the abnormal battery drain happens, the diagnose engine will diagnose what's the root cause. And finally, we have a repair advisor who will tell the user how to fix it. And in the talk, I will focus on the first 2 parts, and for the other details, you can refer to our paper. So let's start with the information collector. So the very important thing about the information collectors, it needs to be energy efficient because we don't want the eDoctor itself become an abnormal battery drain. So how we collect the resource usage, we actually pull data from embedded resource usage monitor, which already embedded in most of the Android application framework. And besides the resource usage information, we also use a very simple usage-based model to calculate the energy consumed in each execution interval. So there are several challenges to do this. First, we need to hack the framework in order to access the data because it's not visible by default. And we also need to efficiently parsing and storing the data to storage. And finally, because of the fragmentation of Android ecosystem, we need to handle many, many different Android devices because they are all slightly different. And to collect the events, we have 2 high-level different strategies. To collect the maintenance events and system-wide configuration changes, basically we capture the broadcast message from the Android system itself. For example, when the user installs a new app, the Android system will send this event android.intent.action package_install. So by capturing this event, and the payload of the event will tell us which app the user installed and the version of that app. And for app-specific configuration changes, it's much more challenging to capture. So what we did is we modified the Android framework so we can capture user changes because the Android framework has certain components which they recommend the developers to use to manage user configurations. So if the developer uses these components and we hack the component, we can capture user changes. However, a clear drawback of this solution is if the app developer uses their own mechanism to manage user configuration, we cannot capture changes, but that's very rare. And the second part is the data analyzer. So basically, the data analyzer will process the raw data and updating phase table for each app. And data analyzer is very energy consuming. So to make this, we don't want this to affect the user's normal usage of the phone. So we only run data analyzer when the phone has external power supply and the processor is idle. So we try to avoid the interference with the user's normal usage. Let me show you a very high level how the data analyzer works. So for example, this table shows 7 intervals we collected from the usage. And first, we run k-mean algorithm to cluster different intervals to different phases. And then we will generate the phase table. So in phase table, we have all the phase IDs, and the number of the phases we have seen in the past, and the total energy consumption of each phase, and the burst timestamp of each phase. So then we use this information to do the diagnosis. And the diagnosis engine works like this. So first, from the phase table, the diagnosis engine can find all the suspicious apps who has the recent new phase and also energy-consuming phases. And then, together with the suspicious app information and the event records, we rank all the suspicious app based on how much energy it consumes, how likely it is suspicious, and whether there is a recent event change on this app. And finally, eDoctor will report the number one root cause to the user. And once we have the root cause, the repair advisor will help the user to suggest the user the best way to fix it. For example, if the root cause is a recent update of certain existing app, the advisor will tell user to roll back the app to the previous version. Actually, because this is not supported by default on Android system, we actually implement an app reverter to help user to do this automatically. Okay, so now you may ask this question. This sounds pretty fancy, but does eDoctor actually work? So to evaluate whether eDoctor works, we conducted a user study where we hired 31 volunteers. They are all regular Android users, and we find 13 real-world abnormal battery drain issues which we can reliably reproduce. And we assign several issues to each user. Basically, for each issue, we implant the issue secretly on their phone, and we let the user run the phone for a week, just regularly. And at a certain point in this week, we will trigger the problem, and the user may observe a battery drain, and the user will invoke eDoctor to diagnose, and they will tell us if eDoctor tells them the right solution. So at the end, we collected 50 valid cases and more than 6,000 hours of really valuable real-world battery usage data. First, we were interested in how accurate eDoctor is. Actually, the eDoctor with RUV schema is very accurate. It successfully diagnosed 47 cases out of the 50. And there are 3 misdiagnosed cases. So there are 2 major reasons for misdiagnosis. The first one is the user started the app with a very aggressive energy consumption. For example, one of the app is a weather bug. It periodically collects the weather information. So while the user installed the app, the user configured the app to update weather information very, very frequently. In our abnormal battery drain case, we actually changed this configuration to be very aggressive. But because the user already configured it to be very aggressive, so when they changed, when the user made the change, we didn't observe like very new phases. And the second second reason of the misdiagnosis is the eDoctor doesn't run long enough to collect normal usage data. So that's a problem of eDoctor in general. But once we widely deploy the eDoctor, we can actually collect the information from many users and a lot of data. So then we can aggregate the information from different users, so this problem can be solved. Another thing we're interested is whether this corporate app always ranked as the #1 energy consumer. Actually, it's not the case. So this figure shows only 16 apps are actually ranked as the top #1 energy consumer. And many other cases, the corporate app actually not the top #1. However, keep in mind, although they are not the top #1, but they still consume a significant amount of energy, which affects the user's usage of the phone. And we are also interested in see how many, actually there are how many phases in the app. And this figure is pretty complicated, but you can focus on the blue line, which is the best algorithm we find to do the phase analysis. As you can see, about 80% of the app has at most 2 phases. And about 90% of the app has at most 4 major phases. Of course, it's a long tail, so there are many other complex apps. They have more major phases, but most of the app has a very limited number of phases. And we also measure the energy overhead of eDoctor, so we use a high-precision energy meter to measure a phone running without running eDoctor versus running eDoctor. And we find that eDoctor introduced less than 1.5% of the energy overhead to an idle phone. So keep in mind, 1.5% is the upper bound of the energy overhead, because once the user actually uses the phone, the baseline will be much bigger and the overhead will be much smaller. And finally, we evaluate the storage requirement of the eDoctor, and we find that the eDoctor with 150 apps installed, it uses 3 megabytes per day. We keep the information for about 7 days, so it uses 20 megabytes. Yes, right on time. So this slide concludes my talk, and one more thing I want to mention is we have a poster in the Thursday's poster session. So if you have if you're interested in more about the eDoctor, you can stop by. And that's my talk, and thank you very much. I'm happy to take any questions.
My name is Everton Cordeiro from Federal University of Rio Grande do Sul, Brazil. Very nice talk. Was wondering about some other scenarios in which your system could work. For example, some time ago, I upgraded my cell phone Android from version 2.1 to 2.2, and also used Cyanogen. And I noticed that my battery started draining more quickly, even though I didn't install any new application. Would you be able to help in that scenario as well?
That's a very good question, because several Android framework actually have battery bugs. In some sense, we can, because we also monitor once you update the overall system version, not only a particular app. So we can still tell you, because of the recent system update, not app update, your battery usage started draining faster. Mm-hmm. But although we didn't have this in the user study, because it's very hard to do this with real user, but yes, we can.
Another thing. Would you also be able to diagnose that the battery itself is dying, for example?
That's a very interesting question. So actually, in our characteristic study, we find the hardware failure, including battery drain, battery die, or the charging cable has a problem. It's very few. But the eDoctor cannot really tell the battery actually is dying, but the hardware failure actually very few. So most of the problems are caused by software problems.
Thank you.
Yeah, no problem.
Thank you. Hi, this is Arash Molavi from Northeastern University. Interesting work. So
Thanks.
my question is, collecting data is one of your main modules in your system. So my question is, and you're basically collecting all users' activity and all network activities and stuff. So is this going to raise a concern about users' privacy? Because you're collecting all their activities. And I guess the second question is, how do you secure all the data that you collect? So, for example, if there's a malicious app or entity cannot access that data.
Very good question. So basically, we don't actually observe what the user do within an app. So we only observe the energy consumption of the app. And the user activity-wise, we only observe the user's configuration change and installing app, all these maintenance changes. So there are still some privacy concerns, but eDoctor doesn't send the data. Basically, the eDoctor doesn't call home, so we don't send the data to our server. So all the analysis and the diagnosis is working locally on the phone itself. Basically, the data will not leak from the phone. And we save all the data in an app-specific storage space, which means other app cannot see this data.
All right. Thank you.
No problem.